morning, students. For those of you who have not met me before, my name is Jamika Marshall, and I am the manager for the Shadow the Scientist initiative. It is great to be with you. Thank you for joining so early in the morning at the beginning of your school day. Sunitha, always a pleasure to see you and to work with you, ma'am. Yes, ma'am. Yes, ma'am. Okay, I know we're getting started a little bit late, so I'm going to jump into it. We have here two amazing science hosts, Garima Singh and Brian Lameau. I will go directly over to Garima and Brian to get us started and jump into the science today of direct imaging of exoplanets. Garima, Brian, welcome.
Thank you. Can you hear us, everybody?
Good morning.
Hello, good morning. So my name is Garima, and I have my colleague here, Brian.
Hi, good morning, everybody. Aloha.
And we are connecting from Hilo. And let me just kind of like start the slide so that, here we go. So we are connecting from the Big Island of Hawaii. So we both are scientists at Gemini Observatory, but today, right now, we are at a different telescope called Subaru Telescope. So we're connecting from Hawaii. It's a state which is roughly 4,000 kilometers from California by air. And it's a chain of, the Hawaiian Islands are a chain of seven, right? 7 islands?
Well,
Seven
depends on
main
how you count
islands.
them, but yeah, can be 1,000, can be 7.
Yes, main island chain. So we are actually on the big island of Hawaii, and we're connecting from Hilo. And there is a beautiful big mountain here. It's a sacred mountain called Mountain of like Mauna Kea. And Mauna Kea is the place where we have biggest telescopes in the northern hemisphere. So this is an image of Mauna Kea, top of Mauna Kea, where you see a lot of telescopes. And so we'll be talking about Subaru Telescope, so which is shown here. And Brian and I both work at Gemini Observatory, which is a different telescope. But both of these telescopes basically are same in size. So the diameter of the telescope is roughly 8 meters. So if you basically take cricket bats, if you take like 9 of them and you put them one after the other, that's how big the mirror of the telescope is, both for Gemini here and for Subaru. So we both work on Mauna Kea, and this talk is about exoplanets. So we would be introducing to you about exoplanets and how do you take images of those exoplanets. Let's begin. So again, on the left side, what you see is Subaru Telescope. Just to remind you again, it's an 8-meter class telescope. And there is an instrument inside this observatory, which is called SCExAO instrument, which I will be talking to you about. And this instrument is basically used to take images of exoplanets. So my job, basically what I do is I develop such technology to take images of exoplanets. And and my goal is basically to demonstrate to you how such an instrument work. So we will be connecting with this instrument remotely. But before I begin, I just want to give you a brief overview of what is this technology and how do you, what are exoplanets and how do you basically take images of those planets?
So, Grima, one question I have is,
Mhm.
does Subaru have other instruments besides the instrument you're going to talk about today? And what is the relationship between the telescope and the instruments themselves?
Great question. So the instrument that I'm gonna talk to you about today, direct imaging instrument, is only one of a kind. Subaru has one, and in fact, we have only two such instruments on Mauna Kea. One at the Keck telescope, the Keck Observatory, which is basically these two twin domes here, and they are the biggest telescope in the northern hemisphere because each of these telescope has 10-meter. The diameter of the telescope is 10 meters. So
That's the diameter of the primary mirror, right?
primary
Yeah,
mirror,
yeah.
yes.
So the domes themselves are much, much bigger.
Yes. So Keck telescope has one instrument. Subaru has one instrument that I'm going to talk to you about today. There's another instrument which will come to Gemini, but maybe in a year. So there's roughly like 3 to 4 instruments on the whole planet which are used to take images of the exoplanets. All right. So the reason I'm talking to you about this instrument today is because I actually helped develop this instrument during my PhD, which I finished about 10 years ago. So I was a PhD student at Subaru Telescope, and I helped develop this instrument. Um, so let's begin and talk about exoplanets. So this is basically what you're looking at is an image of of a sky of a patch in the sky taken by JWST, James Webb Space Telescope. And in this image, you see kind of like at least thousands of galaxies. And one such galaxy is our Milky Way galaxy. And this one is a real image, but this one is an artistic impression of how our Milky Way galaxy looks like. So, our Milky Way galaxies had 300 to 400 billion stars, and one such star is Sun, and Sun is roughly 20,000 light years from the center of the Milky Way. And light year is just like a unit that we use to basically explain how much distance light travels in a year. So in 1 year, light travels about 9.46 trillion kilometer. So Sun is roughly 26 light years away from the center of the Milky Way galaxy. And I'm sure most of you know Sun has at least 8 planets around it, right? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto is not a planet anymore. So in our solar system, around this our star, Sun, we have 8 planets. And I kind of like to show this image because we have mostly explored all of these planets in our solar system. Um, so what is a planet? Before I begin and talk about exoplanets, so there's like a current definition of what a planet is, and it kind of like it keeps on refining, every time we have like a new discovery of an exoplanet. So for now, a planet is a body that should be, orbiting around a star. It must have enough mass. This body must have enough mass to basically create a round shape under its own gravity, and this body must be a gravitationally dominating body in its neighborhood. So, like with when Earth has Moon is gravitationally bound to Earth, right? But Moon is not gravitationally dominant; is Earth. So Earth is a planet, and Moon is not. And any planet which is bigger than 13 times the mass of the planet Jupiter is not a planet anymore, it's a brown dwarf. So that's like a general definition of a planet. So we have 8 planets around our star, Sun. Now let's go back to this image of the Milky Way. NASA statistics says that each of the stars that we see in the night sky has at least one planet orbiting it. So a planet, so no, I told you like we have roughly 300 to 400 billion planets in our, sorry, 300 to 400 billion stars in our Milky Way galaxy. So we are talking about 300 to 400 billion planets. So a planet which orbits a star other than the sun is called an exoplanet. And if you go to this NASA website, you will see a number which basically tells you how many planets we have, exoplanets we have confirmed. How many of them do we know exist? And today, as of like 14th of June, we know roughly 6,000 exoplanets only in our Milky Way galaxy. All right. Um, so and this is like a video, which I'm not going to show here, but I've shared these slides with your teacher, so you can see this video later on. This kind of shows you, again, an artistic impression of the Milky Way, and we are looking at our galaxy edge on. And all of these dots that you see basically tells you where have we found those planets, those exoplanets in the night sky. And on like up here, it tells you like, there are several ways of finding these planets, and I'm gonna just introduce two to you today. And these kind of tells you which technique, which method we have used to find what kind of exoplanets, right? That's not the topic. We're not gonna go into details, but this was just to kind of show you visually where are those exoplanets in the night sky, with respect to our Milky Way galaxy. All right. So I'm gonna basically introduce you two techniques through which you find these exoplanets. One is called transit technique. So this is basically an indirect way of finding a planet. So you can imagine this is a simulation. This is not the real uh, images here. So if there are like couple of planets orbiting a star, right? And if they fall in our line of sight, if a planet passed through in front of the star, it will block some part of that starlight. And we can actually measure the brightness of the star when there is no body passing in front of it. And when there's like few bodies pass in front of it, they will block a chunk of the star. And you can kind of see these dips in the brightness of the star. So we can like study such a plot, and we can like see these dips, and we can figure out how many planets are there in that extra solar system, how far or near they are from their star, or how big or small they are. So you can actually get this information alone from this kind of data that you can receive, that you can actually collect from your telescope. So this is called transit technique. Um, and so in this technique, you don't see the planet, you just basically infer the presence of a planet uh, uh, by monitoring the star itself. So this technique was very successful in finding most of the exoplanets that we have discovered today, like roughly what 6,000 I mentioned, right? And this technique has given us more than 4,000 exoplanets, but we don't see it visually, in our camera. The one that I work on is called direct imaging, which means, as the name suggests, you actually see the image of a planet. So we basically point our telescope to the night sky, to this, a star, and then we can actually take the images of those planets. So in our camera, we can actually see where the planet is after a bunch of post processing. It's very difficult to see images of planet with your naked eye. So let me explain you like how direct imaging, how do you take images of these planets? And so there's a technique. So for example, what you're looking at, again, it's a simulation, right? You're looking at a simulated image of a star. Planets are extremely dim. They are roughly 1,000 to 10 billion times fainter than their star. So it's extremely difficult to see such a faint object around a very bright star. So if you look at a star image in your camera through your telescope, you can't see anything. What you need to do is block the light of the star. Once you block the light of the star, then the image of the planet, it becomes visible. Before blocking the light of the star, the image of the planet was hidden underneath, the image of the star. So this technique where you block the light of the star inside your instrument, this device is called coronagraphs. So this is what we're gonna talk about today. Um, what is coronagraphy, and how do you block the light of the star and see the image of a planet? So, all right. So I'm gonna just repeat myself as I said, just to kind of like give you more visual, understanding of what it means when a planet is extremely dim in front of an overwhelmingly bright star. So the analogy that we like to give is like you have a bright lamp. And if I basically tell you, oh, there's a firefly sitting somewhere on this bright lamp, and I'm like, oh, tell me if you can, if I ask you, like, tell me if you can count how many fireflies are sitting on that bright lamp, you'd be like, well, we can't see anything. It's just like you're blinded by, the brightness of this lamp. So if you turn this off, then maybe, there's a firefly which was sitting over there, and then you basically see it because now you can see more clearly because you're not blinded by, this brightness of this lamp. And that's what precisely what we're trying to do. We're trying to isolate the light from the planet from the light of the star so that we can actually extract the signal from the planet, and then we can study, that planet. We can study the atmosphere of that planet to see what is the composition of the planet, like what is it made up of. Another way to understand the same thing is like in this image, what you're looking at, it's during the solar eclipse. What happens during the solar eclipse? What you have is like, moon comes in front of the earth and the sun, right? And then when basically moon is blocking the light of the sun, if you have seen, solar eclipse, you could see actually that when moon completely blocks the light of the sun, then you can, if you're lucky, you can see the image. You can see some of the brightest stars and the planets of our own solar system during daylight, when moon has blocked the light of the star, of the sun itself. So this is not a real image, this is a simulated image. Here's the moon blocking the light from the sun, and then you can see, if you're lucky, you can see some bright stars during daylight. So that's exactly what we are trying to do. We are trying to physically block the light of the star of other extrasolar systems so that we can see planets around them. So there was basically this French astronomer who actually discovered this technique. So, back in like 1930s, the astronomers, they would have to wait for solar eclipse to happen when they wanted to study the corona of the sun. you know so they would chase the solar eclipse so that they can take images of the blocked sun and then study the prominences, the corona of the sun. So this French astronomer was like, well, you know what, I'm not going to wait for the solar eclipse, I'm not going to chase solar eclipse, I'm going to create a device, I'm going to put it inside my telescope and block the light of the sun directly in my instrument, and I'm going to look at the sun, observe the sun and the corona of the sun during the daylight. So that's what he's doing on the left side of the image, where this French astronomer is observing the prominences of the sun during the daylight, because he managed to block the light of the sun itself inside his telescope. And this is an image that he took where you see this black dot, if you can see, that's the planet Mercury. So and the sun is here and it's blocked inside the telescope, and you can kind of see the corona of the sun. So this is exactly, again, to explain you, this is exactly what we are trying to do. We block the light of the star inside our instrument so that we can see planets of that system. Um, so here, just to give you another example, here I'm going to play the video. Sorry. What you're looking at, in the middle, there's a star, and we block the light of the star. And if you look at these four moving dots, these are real exoplanets. This is a system which is very, very far away from us. I kind of forgot, it's like 116 parsec away from us, this extrasolar system. And this star has basically
So
four
350
light years.
about,
Yes,
yeah.
350 light years roughly.
And it's also worth noting the timestamps on the bottom left there.
Yes, exactly.
Yes, this is over the course of years
Yes.
that these observations were taken.
Exactly. Thanks for pointing that out. So this is the data from 2009 to roughly 2015. You have to basically take the data, you have to look at the star planet system years after years so that you can see these planets in motion. And these planets are basically extrasolar giant planets. They are way bigger than Jupiter, and they all are gas giant planets. So this is not a simulation. You're looking at a real star planet system. And the black dot here at the center, this is where we block the light of the star. So I'm going to show you when we're going to demonstrate this technology in the lab, how you move this inside the instrument. All right, so that's one thing with direct imaging. We need to first block the light of the star. But before we do that, there's another problem we need to solve. The other problem is the Earth atmosphere. So, the telescopes that we have on the ground, they look through the Earth atmosphere. When we look at the star planet image, we are looking through the Earth atmosphere. Looking up through the Earth atmosphere is like looking down in a swimming pool filled with water. So here's an example just to kind of show you. There's like a bunch of little fish or animals in the water. They're moving around and they're creating turbulence in the water. And there's like sunlight coming in and it's refracted, and you kind of see how this movement, because of the fish, is making the water moves, all the different layers of water move, and it's making the light refract. And what you see at the end, at the bottom, is a very speckly image, kind of moves around. So looking up through the atmosphere is kind of like looking down in a swimming pool. So another way to explain it is like the light, this when it leaves the star, it basically travels in plane waves. And the moment it enters the Earth atmosphere, it meets layers of different temperature, and different wind speed, and it creates basically these different layers have like different index of refraction, and it makes the starlight refract a lot, and that's what causes stars to twinkle. We don't like twinkling, when we're trying to find planets around other stars, because remember, first I told you we need to block the light of the star. Now you can imagine, how would you block the light of the star if the star keeps on moving, right? So this is a video of a star, a real star, through an 8-meter class telescope, and you kind of see how it moves, the image of the star. Kind of like similar to how the sunlight is basically, is speckly and moving at the bottom of this giant tank here. So what we need to do before we can block the light of the star, first we need to untwinkle the star. What it means is that we need to make the star untwinkle, we need to stabilize it. And how do we do that? We use a technology called adaptive optics. So let me explain to you what adaptive optics is, and then we will go in the lab, and then we'll do some demonstration. So it's exactly what I was just telling you, when the light waves basically leave the star, they basically, a star is emitting light in spherical waves, and then, it coming from us from infinity, and by the time it reaches us, those waves become plane. And if when there is no Earth atmosphere, we can take those plane waves, and then we can use a lens to focus, the light wave, and it will create a very nice crisp image of a star when there is no distortion because of the Earth atmosphere. When you introduce the Earth atmosphere, these plane waves become distorted. And what happens when you try to focus these these light waves through a telescope? They no longer come to a focal point. So what you see is like a blur of light. You don't see like a crisp image of a star. This is exactly what I was saying before. The twinkling of the star basically makes everything kind of like chaotic. So we need to go from this speckly blur image to a crisp image of a star, and we do that using adaptive optics. So just to kind of like recap, for direct imaging, we use coronagraphs to block the light of the star. But before we can block the light of the star, we need to basically have a stabilized image of the star, untwinkle the star, and we do that using adaptive optics. So what is adaptive optics? So it's going to get a little technical, but don't worry about the terms here. Adaptive optics is just a technology which has like these three components. It has a wavefront sensor, it has a control system, and a deformable mirror. Before I explain what these things are, let me give you an analogy. When you take shower, right? And let's say the water coming out of the shower is very hot. So your body basically senses what is the temperature of the water, right? Then your mind immediately sends signals to your hand, oh, I need to turn on the cold knob because it's too hot, right? And immediately, you use your hands to, adjust the temperature of the water so that you can have a nice shower. This is like a simple way to explain what adaptive optics is. So wavefront sensor basically senses how much light is deviated from those plane waves. What is the distortion in the plane waves? That's the job of the wavefront sensor. Exactly like how your body basically senses the temperature of the water in the shower analogy. Control system is basically is something I'll explain you later. It's just it's just a way to compute the it just does some mathematical computation. I'll explain that to you later. Once you senses what is like how much light is deviated from the plane waves, you basically use a technology, this device, which is called deformable mirror. This device basically undo the deviation, so it makes these distorted plane waves flat again. So this is a very important piece of technology, deformable mirror. So this is basically acting out as hands in our shower analogy. So basically, a wavefront sensor senses how much deviation there is in your wavefront, and this piece of device, deformable mirror, basically undo the effect of the Earth atmosphere. And this device is very important because this is just a piece of mirror supported by a bunch of actuators, And this piece of mirror, you can change the shape of the mirror to change the shape of the light. So we are basically, this device, what this is doing, we are going from this distorted distorted waves to plane waves so that we can have like a nice image of the star. So that's what adaptive optics does. I'm going to play a video and it will be more clear. Do you want to say something?
No, I just wanted to ask one question. So in
Okay.
your shower analogy, I mean, if you act really like, so if the temperature is really hot and you're really motivated, maybe you get that whole process done in half a second or so. So you sense it, your mind says, okay, things are going wrong, and then you turn the shower handle. How quick does this process work for the AO system?
That's a wonderful question. So all of this process, it happens like 1,000 times a second. Basically, 1,000 times a second, a wavefront sensor is measuring what is the distortion in the plane wave, and then the deformable mirror then, it changes its shapes 1,000 times a second to basically make those, distorted plane waves back, distorted light waves back to the plane waves. So it's measuring and correcting everything very fast.
So that's why we saw the shimmering in the
Yes,
mirror that was
exactly.
happening.
So let me
you can almost not even tell it's not.
exactly.
That's a thousand second.
Yes. So if you can see, like this is a mirror, which is actually, you may see that it's kind of like moving because it's moved by a lot of actuators, which is holding this surface.
Little pistons in the back that are moving the mirror.
Exactly. And you can actually fit 4 1 rupee coin in the diameter here. This is just to tell you the size of this thing. And excuse me, these devices are pretty expensive. It's like a rough, like $500,000. Like these devices are very, like extremely expensive to handle. But that's the main component which basically untwinkle the star. So to summarize everything before we go in the lab, let me show you the video. So in this video, the light from a star is coming, right? And then you will see this kind of like potato chips are explaining, like, it's just a wavefront of light. And then you put a coronagraph inside your instrument at the focal plane of the telescope. And then you will see kind of like the brightness of your image kind of reduces. So you're blocking the light of the star. The light of the planet, when it comes in, it doesn't pass through the coronagraph, so it's not blocked by the coronagraph. And now you have your wavefront sensor, which is sensing how much there is a distortion, and this is your deformable mirror, which is correcting for the distortion in your image. And with time, you see kind of like the star is completely blocked, and you have the image of the star, image of the planet kind of emerging in your camera detector.
So I have a quick question, Garima. So you're taking an image of the star, but you're also using the light to measure corrections in the wavefront. So how is it possible that you're both taking an image of that star and also using the light to calculate corrections?
That's a great question again. So inside our instrument, we have something called beam splitter. So we basically send some part of the light to another channel, which is used to do the wavefront sensing. And the rest of the light is then, we let the light go through the camera where you're taking images. So we split the light and we send some light to the other arm of the instrument just to do the sensing. And the other half goes to the imaging where we are taking the images of the star.
So SCExAO is a infrared instrument, is that right?
So yes, it has both visible and infrared component to it.
Okay. So some of when it's imaging in the infrared, most of the visible light goes to the deformable mirror, to the wavefront sensor.
Yes.
And then when it's invisible, some portion that it's not sensitive to, of the visible spectrum goes to the wavefront sensor.
Yeah.
So you're not taking any light away from the instrument that it could actually measure.
No. So actually all the visible light goes to the wavefront sensor, and the infrared light goes to the infrared detector where we are taking the images of the planet. And the reason we actually take images of planet in an infrared, because these planets, they are warm, they're emitting their own emission, and it's easier for our instrument to see those planets. For example, if you ask me, like, can you take images of exoplanets in visible light? No, we can't, because they're extremely dim and they don't create their own light. We like those planets which create their own light, because we are the instruments basically are sensitive to finding those planets more, which glow basically. So that's why we basically image in infrared. Our instruments are designed to take images of exoplanets in infrared. That's the reason we're imaging in infrared. So let's see. So this is kind of like just to show you real images, of some of the real nice images of planets that we have taken from some of the biggest telescopes of the world. So, this is a planet. If you go line by line, you will see in each row, this is a planet, started in 2014. And then we've taken images for like 4 years, and you kind of see this planet in orbit. So it's kind of like start to go behind the star, because it's orbiting this star, and then you can see, like, in 2018 it's emerging out from the other side. And
This was taken from the southern hemisphere, right? So
Yeah,
this is from a
exactly.
very large telescope array
Yeah, it's
in Chile.
Yeah, it's a different telescope, by the way. This image is not from Subaru Telescope. It's another telescope which is called Very Large Telescope. It's in Chile, in southern hemisphere. And
More or less the same size telescope.
exactly, yes. And so other than taking images of these planets, you can also actually take images of the circumstellar material around the star, which these planets, they use to basically form and evolve. So this is basically, it's all gas and dust. And at the center again, this is the star, which is actually blocked by the instrument, by the chronograph. So you can not only take images of these planets using, the technology that I explained to you, but you can also see the birthplace of these planets. Now I'm gonna basically, how much time do we have? Okay, we have, okay. We're
Well,
good?
25 minutes.
Okay, well, we're
About 13 minutes, so maybe 10 minutes.
10 minutes. Okay. So can you see me? Can you see the telescope here? All right. So let me quickly explain you. Basically, this is a Subaru telescope, which is the 100 times smaller than the real telescope. And so the light basically, let me just hold it like that. The light, thank you. The light comes from the universe, right? And then the primary mirror is here. It bounces from the primary mirror, goes to the secondary mirror, and then from the secondary mirror, the light is focused inside this tube, and then it goes underneath the primary mirror. So you can put your instruments either below the primary mirror for this telescope, or you can put the instrument here above at the back of the secondary mirror, or you can send the light on the side, which is called the Nasmyth platform. So the instrument that I'm gonna quickly demonstrate to you is actually sitting at the Nasmyth platform. So let me show you, just to give you an idea, like, here's a video that you can watch later. Here's the Subaru telescope here. And you see my colleague is gonna actually walk on the side, and he's gonna go to the platform where the instrument, the SCExAO instrument is, the instrument that I'm gonna quickly show you in the lab. So that's where the instrument is, just to kind of show you the size of a human being with respect to these instruments that we work with. So here, what you're looking at, this black box, this is where the input from the telescope comes in. This black box is the adaptive optics instrument that I just explained to you. And this box here is the SCExAO instrument, where we have all the coronagraphs to block the light of the star. So this is how the SCExAO instrument looks like. So what I explained to you, it's a very sophisticated technology. If you open this box, basically, this is how it looks like. This is what it takes to basically untwinkle the star and then block the light of the star and then see the exoplanets. Now, let me quickly take you to the lab. So we are basically, sorry. Okay, all right. So we are basically in the lab here. So what you're looking at, the wavefront sensor that I just talked to you about is here. You don't need to understand everything on the screen, but what I'm showing here is that we have created in the lab with the laser and a simulated image of a star. It's a fake star here that you're looking at, right? And now let me introduce some turbulence that we basically see you know, through the when we point a telescope to the night sky, we see kind of like the image of the star is all distorted. Let me actually do that in the lab. So I've turned on the turbulence in the lab, and now you can see like, how this image of the star, which was stable before, now it's moving, right? Let me actually zoom in here. You see how it's moving, right? And it's no longer stable. Let me also increase the strength of the turbulence. So I can actually choose the number here. I can choose like, okay, let's increase the wind of the speed to 15 meter per second. So now you may notice like how it start to kind of like move a lot, right? I can like I can increase the speed of the wind. I can, increase the strength of the turbulence, right? And when so you remember I told you like wavefront sensor basically measure how much aberration is there. So that's what this wavefront sensor is doing. It's measuring continuously how much turbulence is there in this image. Now I'm gonna turn on the loop with the AO, which means that I'm gonna tell the deformable mirror, okay, now it's your turn to start correcting this image, right? So here we go. I'm gonna do it. Just pay attention to this image here, okay? I'm gonna tell the deformable mirror, correct the image now, and see, you see how it became all stable again? Did you notice it? Yeah, let me stop the deformable mirror, and you see how it's kind of started to move again through the earth, through the simulated earth turbulence. And now I'm gonna, we close the loop. So we tell the deformable mirror, oh, all right, do your work. So it has started to, did you see what happened? It moved a little bit. Maybe somebody was walking where this instrument is, and it created vibration, and that made the image move, right? Now we have like turbulence, full turbulence on. We have like deformable mirror taking care of the turbulence. Now let me actually put the chronograph in. So so what I'm doing basically, I'm moving different optics inside the instrument, and it's actually moving. Maybe let me show you a filter wheel. So there's an optical unit which is called filter wheel, and this is actually moving, and it's selecting which chronographs to put because we have a lot of chronographs on this instrument. Did you see how the coronagraph came in the view and it blocked the light of the star? Let me increase the exposure time for you to kind of see it a little bit more clearly. Did you see like how like we just moved the chronograph in and then we blocked the light of the star? Unfortunately, I can't simulate a planet. So if there was a planet, it would be visible after we put the chronograph in. So now let me just kind of like show you one more thing. Let me tell the deformable mirror, don't do any correction. So you see, chronograph is still there in, but it's not doing a good job in blocking the light of the star. So if there is a planet somewhere here, you won't be able to see it with your eyes, right? So that's why adaptive optics technology is super important to take direct images of exoplanets. So if I tell the now continue, like notice here again, when I'm going to tell the deformable mirror, start the correction, which means every 1,000 second, it's actually applying a correction. And you see, once I do it, it's like the turbulence is still on in the lab, and the deformable mirror is sensing, the aberration and correcting it right away, while the star is blocked behind the chronograph. And so this is like the main ingredients of how you take like direct images of exoplanets. Unfortunately, I can't simulate a planet right now here, but this is just kind of to demonstrate to you that we do a bunch of testing in the lab during the daytime to test all of this technology before we go on sky at night and then have look at the real star planet system and start taking real images. So after this, basically, normally you don't see a planet right away. We need to do a bunch of post processing to be able for us to see clean images like this one. But this is basically how we do it. And I think I just want to kind of like leave some time for some questions. So, um, Jamika, if you want to take over and then basically see if students have questions.
First, this was amazing. This is my first view of SCExAO in action, simulated in action. It was brilliant. We have about 4 minutes before the end of this session. So, Sunitha, do the students have questions that you'd like them to ask now? And if so, please go ahead.
Yes. My question is, are there any instances of brown dwarf found in the universe? Come closer to the microphone. Are there any instances of brown dwarf found in the universe that man talked about? Brown dwarf.
Brown dwarfs? Like, have we
Yes.
found brown dwarfs? Is that the question?
Yes.
Is that the question, right?
Yes, ma'am. Yes.
Okay. Oh yeah, we keep on finding bunch of brown dwarfs when we take images of exoplanets, because once we take an image, we need to basically measure its mass to be able to basically see if it's a gas giant. Is this planet like, bigger than 13 times the mass of Jupiter? Because if it is, then it's a brown dwarf. So there's like, we keep on finding more brown dwarfs than exoplanets, unfortunately, with these instruments. Because bigger is the planet, the easier for us to see it. Smaller is the planet, it's very difficult for us to see it.
Right. So that's a selection effect, right? So the those are the easier ones to find. So it's not necessarily the case that in the universe there are more brown dwarfs than there are lower mass planets, but it's just easier for us to detect them.
Yes, exactly. Yeah.
Great question. I think we have time for at least one more.
Ma'am, what is the scope of discovering exoplanets?
Scope of discovery.
Exoplanets.
Scope of discovery of exoplanets. Scope. It's a good question. So basically, if I understand this question correctly, what are we trying to do is, in the end, we want to basically find life on other planets. So we want to basically understand, we want to have more and more data on the atmosphere of these planets. And how do you get the data on the atmosphere of these planets? One technique is do the direct imaging. And we want to basically have as much data possible to understand what is the physical and chemical composition of these atmospheres, so that we can actually figure out, answer the final question of whether there's life on these planets or not. Is that what it is, like scope of these planets? I think exactly.
Yes,
So Brian reminded me about this telescope called Habitable World Observatory, HWO, which hopefully will be launched in 2040s. And this telescope will target finding Earth-like planet, invisible light, basically. So, and the idea again is to find Earth 2.0. That's the ultimate question that we all are trying, like we exoplanet imagers or exoplanet finders are trying to that's the main motivation why we are actually hunting these planets.
So maybe one more question.
We just wanted to know, ma'am, which telescope you work directly on? Which telescope you develop directly?
Which telescope we work for?
Yes.
Gemini Observatory, which is like the office is actually just next door. So we are in the Subaru office. So all of these, offices are kind of like at the Hilo base facility, and they're in the university area. But the telescopes themselves are on the mountain, and they're also side by side.
Name of the mountain? Name of the mountain. Name of the mountain, right?
Hard to understand.
The name of the mountain.
Name of the mountain is Mauna Kea. And Mauna means mountain in Hawaiian, and Kea means snow. So it's a snow mountain. And it's actually a sacred mountain, just like Himalaya in India.
Yes, thank you so much. Thank you.